So the last topic we're going to discuss here is how to configure the common fork join pool for a parallel stream and what the benefits of doing such a thing are. And this would also be relevant if you're configuring a common fork join pool for a non-parallel stream, just in general. So we're going to show why it helps to add threads to the common fork join pool. And this is in the EX20 folder on my account. So as we've discussed a number of times, the common fork join pool size can be controlled programmatically. This demo will apply the ManagedBlocker interface that will allow the threads to be added dynamically as the program runs. And we've talked about that. We talked about how ManagedBlock worked and ManagedBlocker worked with the ManagedBlock mechanism on the fork join pool. So you'll get a chance to see how this all behaves. The driver program is very cool and very abstracted. What we're going to do is have this little method called test download behavior, and we're going to pass it a function. And as we'll see in a second, that function will do various means of being able to download files. And so as you'll see here, we're going to get a parallel stream. We're going to call that function in the parallel stream to download the files. Some variants will not do anything to the fork join pool at all. It'll just keep its default size. Other ones will adaptively add and dynamically add more threads to the pool. And then we collect the results and print the statistics. When we run the program and see the results, they're really interesting. So when the program starts to run, it tells you how many cores the computing system has. I'm running this. I have run this on my 6-core laptop, which has hyperthreading, so the virtual machine thinks it's 12 cores. We first run this thing downloading 42 images using the default number of threads in the pool, which is 12. Then we go ahead and do 2 different variants that use the ManagedBlocker to add new threads to the pool as threads block. And because they're downloading images, they'll block. And the images are rather large, so they'll definitely block. And you can see here, what we do is we basically end up adding a new thread to the pool for every image that's downloaded. So we end up with 43 threads in the pool for both of these versions versus the default number of 12. And then when the whole program is done, it'll print out how long it took to run. And it sorts them from fastest to slowest. So you can see here that the one that used the blocking task, which I'll show you, we've talked about that before, that one executed in about 3,600 milliseconds. The ManagedBlocker one ran at about 3,900 milliseconds. And the default version that had only 12 threads ran the slowest in 4,100 milliseconds. Now, these are not wildly different performance results. The point, though, is that by having more threads, it'll work better. And you would also expect, for instance, depending on how your computer system worked and the sizes of the images and how long they took to download, you would see variation because the longer these things block, the more you're going to get a win from having extra threads in the pool. So if you're downloading very large images that will block for a long period of time, adding more threads definitely will improve the performance. So let's go ahead and take a look at the code for this. So here's the test program that runs this stuff. It's called EX20. You can see it just goes ahead and makes an instance of the EX20 class and runs it. The run method warms everything up, and then it goes ahead and runs a test using the default behavior. We'll look at that in a second. And you can see it passes in a method reference, which is just called download and store image. That has no adaptive behavior, doesn't change the size of the fork join pool at all. We then run the test again, except this time we pass in a method reference that will explicitly use the ManagedBlocker interface in the ManagedBlock method. And then the last thing we do is we run another variant of that with another method reference that uses the blocking task implementation. So let's take a look at this. Here's the run test method. This is the one we use to run all the tests. Run test is basically just a test harness that will call the test download behavior method, passing in the function parameter here, and it'll time how long it takes to run. And I wrote this cool little timer class that does some neat things to help time the results and sort them in their fastest to slowest order. Here is test download behavior. This is the thing that's doing all the processing. As you can see here, it deletes the images if there were any downloaded before. And then it goes through all the URLs that we have. And I ended up with 42 URLs that are on my website that I use for this. And then in parallel, it will download and store them. And download and store image is this function that's passed in here. And as you saw back up here, it was passed different method references to evoke different behaviors. So one behavior, this one here, doesn't do anything to the thread pool size. The other two do. So this thing will go ahead and download the image with whatever functions passed in, and it collects the results into this list. So here's the default implementation. This just does download and store image. As you can see, all it does is it simply downloads the image at the URL and stores it. So that's all it does. There's no modification to the thread pool, common fork join pool size, no changes at all. In contrast, here's the download and store image MB for ManagedBlocker. And this does some rather interesting things. So what we do is we go ahead and call the ManagedBlock method in the fork join pool. That's a static method. And we create ourselves a new anonymous inner class of type ManagedBlocker, or it's an implementation of the ManagedBlocker interface. And all the magic goes here in the block method. So you can see what block does is it calls download image and returns true. And because it's using a ManagedBlocker, that will automatically cause the common fork join pool to expand. So this version will actually expand the fork join pool, whereas the version up here does not. And when it's all done, we go ahead and store the image. The only downside with this approach is it's a little bit crufty and awkward to program. So I have another implementation called download and store image BT, which uses the blocking task class. And we've talked about blocking task in other discussions. And what this does is this wraps up all of this kind of stuff here into a nice little decorator. And all you do is say blocking task call in ManagedBlock, and you give it a lambda expression, in this case a supplier lambda, which we're going to use to download the image. And that will then magically use the ManagedBlocker under the hood to do all the work. And here's the download image method itself. As you can see, it just goes ahead and takes the URL and it downloads the content. And all that does is it just opens up the file, or it opens up the URL and then just downloads the content and converts it into an image. So the key takeaway point of this is that by having more threads in the pool, then under the right circumstances, you can get better throughput. That's the key point to understand. Okay.